everybody, and welcome. We're going to get started in a few minutes here. We're just adding a few more people as they come in. I'd like to welcome you back to our fourth UCO Ask-an-Astronomer as part of our virtual series. I'm very happy to introduce you to Brian DiGiorgio here, who is our kind of resident Ask-an-Astronomer person who works up at UCSC. He's a postgrad student and he's been there since 2017. He regularly mans the email and the website answering people's questions as they come in. And so that's where this kind of series was birthed from. And this is where this series of Ask-an-Astronomer will return home to when we no longer are doing it so often as a virtual event. So with that being said, I'd like to turn you over to Brian and he'll say hello and then we'll get started with the first question.
Yeah, hello everyone. As Marianne said, I'm Brian DiGiorgio. I'm a PhD student up at UC Santa Cruz in their astronomy department. And you know, a few years ago, I volunteered to staff this email address, and a few times a week, I'll get some question from some person in some random corner of the internet asking, what was that thing that I just saw in the sky? Or can you tell me more about this thing that I heard about in a news story or something like that? So I've gotten a lot of practice of answering very off-the-wall questions from curious people who seek out astronomers on the internet. So I'm excited to answer the questions that you guys have today.
Okay, so the first question we have up here is from Amelia, and that came via our social@ucolick.org email. And she asks, can you please talk about the recent comet, Neowise, info about scheduled things to look for locally in the sky?
Yeah, so I'm sure that most people in the in this chat room have heard about the comet in the past few weeks. It's been a very notable astronomical event and a good thing to do while social distance in the pandemic in your own house. Unfortunately, the comet is kind of on its way out now. It swung around the sun a few weeks ago and got really bright and got those nice, got the nice tail that you saw long pictures of, and it's been slowly getting further and further away from the sun and the earth over the course of the past few weeks. So it is still possible to see, and if you have a pair of binoculars, I would recommend going out in the next few days as long as it's clear and looking kind of below the Big Dipper in the night sky just after it kind of gets dark. You know, the darker the better. You're looking over in the north, kind of low towards the horizon, below the Big Dipper. And if you kind of scan around for a little bit, you might be able to see still a little puff ball that has a tail kind of extending upwards from it. And it's a really cool thing to see. It's definitely the most impressive comet that I've seen. Although, you know, I wasn't around for the comet in the 90s that was much brighter than this. So anyways, it's kind of past peak at this point, but it's still a good thing to go out and look for below the Big Dipper just after it gets dark. Okay,
so moving on to our next question, and this one is from Ron Roman, and again, that's via our email address. He is asking why he typically sees measurements of galaxies described in terms of their width. And he says he does not recall reading about the depth of galaxies. So why just widths and not depths?
So this is an interesting question. Usually people will say like, oh, the Milky Way galaxy is 100,000 light years across, but you don't really hear about how thick it is. And you can kind of think about this question too, if you've ever been in a dark enough sky that you could go outside and see the Milky Way. It looks basically just kind of like a pretty straight line, flat band in the sky. And you don't see a lot of Milky Way galaxy that's kind of outside of that one plane. And the reason for that is that if you actually look at a typical galaxy edge on, it's basically a flat pancake. So I'm going to, oh, Marianne, can you turn on screen sharing for me?
Oh.
Well, I can talk about this. So a typical spiral galaxy like the one that we live in, the Milky Way, is a pretty wide circle, but it's very narrow in most of the parts of it. So this is a slightly different type of galaxy than what we are used to, or than the one that we live in, but this is called the Sombrero Galaxy. And it's called that because it looks like a nice flat, wide-brimmed hat right here. We live kind of in the middle of these dust clouds that are this very flat disk. And the area of the Milky Way that we're in, it's about 100 times, it's about 100 times thinner than it is wide. So this is about 100,000 light years that goes in this direction, and the disk part of this is only about 1,000 light years thick. So if you're asking about, why don't we hear about the depth of galaxies, or is like a two-dimensional image kind of accurate for these? It's basically spiral galaxies are flat circles, and a lot of times astronomers for research purposes even treat them as basically just a flat, infinitely thin disk. So it's usually a good assumption.
Okay. Next question. So this one's from Jenny Troy, again via our email address. If you could go anywhere in the universe, where would you go and why? This
is a really fun question. I like this as a question, and I thought about it for a little bit when I saw this. And I think I have kind of three answers that are a little bit different from each other. So I think the first place that I would choose to go would be the middle of a star-forming nebula, like the Orion Nebula. This is a really cool picture that somebody has kind of, taken and edited to bring out all of the different colors that will be present in a nebula that is currently collapsing to form stars. So this is the Orion Nebula, which is just below Orion's belt in the winter sky. And you can see all of this pink and blue light here are different glowing elements that are being ionized by the super bright stars that are at the center right here. And so if you were to be sitting in the middle right here, you would see clouds of gas and dust. Your eyes might not be sensitive enough to actually see that they're red, but you would still see kind of these shining clouds and super bright stars as they were kind of condensing out of this interstellar gas. So that would be a really cool place to go. Right now, this Orion Nebula is a little tiny speck in our sky that you need binoculars or a telescope to get a good look at, but it would be cool if it could take up the entire sky. The next place I would like to go would be the center of a globular cluster. So globular clusters are these kind of dense, packed snowballs of stars that are orbiting around the centers of most galaxies. And they have massive amounts of stars packed into a tiny area. So the star density, like the amount of stars per unit space in the center of a globular cluster, can be hundreds of times what it is in like in our local solar system area. So if instead of looking up and seeing like, the amount of stars that we see, you could expect to see like thousands of times more. And I think that would be a crazy thing to see. It would probably not even be totally dark at nighttime if you had all of these different suns that were so close shining down on you when you were there at night. So that would be a really cool thing to see. And the last place, kind of continuing the theme of going into the middle of where new and interesting things are happening, I would like to go to the center of the Virgo cluster, which is the nearest galaxy cluster that we're part of, and we're part of kind of the outskirts of the Virgo supercluster. But near the middle of this, there are all these galaxies that are packed into a tiny area. So in the distance between us and the Andromeda galaxy, you would see many, many more times the amount of galaxies than we see in our local group. And so that would be really cool to be able to look out into the sky and see different galaxies with your naked eye, and see lots of them all over the sky in this dense cluster. So yeah, I think that the places that I would like to go in the universe are kind of the centers of activity that you would be able to see all of these things that we kind of on the outskirts of our galaxy and our supercluster have to use a telescope to look at.
Oh, thank you, Brian. So the next question is from Marlene Huffaker, and she asks, if I were on a planet in a galaxy 13.7 billion light years from Earth and I looked out into deep space in all directions, would I likely see a deep panorama of galaxies in all directions, or would I be close to the edge since all distant galaxies are traveling away from one another? Can we locate where in the universe the Big Bang occurred, and if not, why?
So this is a question that I've actually gotten before on the Ask-an-Astronomer email address. And the way that I usually explain it is by using a popular metaphor in cosmology, which is to think of the expanding universe like a balloon. So here's a picture to kind of help out with this. So imagine that you are sitting on the surface of a balloon and you hear that the universe is expanding, and that means that somebody is blowing into the balloon and making it bigger and bigger and bigger. So you standing on one part of this balloon right here, looking at, a galaxy on the other part of this balloon, as you blow the balloon up, those two galaxies are going to get further and further apart from each other. But if you were to kind of ask, like, where is the expansion actually coming from? It's not from anywhere on the surface of the balloon. Like, no one of these galaxies is expanding outwards to drive all of the rest of the galaxies. It's just the space that you're living on, the surface of this balloon, is getting bigger as somebody is blowing into it. But so as you're on this two-dimensional surface that is being stretched in all directions equally, there isn't really a center on this two-dimensional surface. You have to go into an extra dimension to see where it's actually expanding. And this analogy isn't perfect. Current models of cosmology don't think that the universe is curved like a balloon is. They think that it's more flat. So really it would be kind of a rubber sheet getting stretched equally in all directions rather than a rubber balloon getting blown up in a sphere. But it's a good thing to consider in terms of, like, we don't live in a high dimensional enough space to really think about there being a center, because the center is kind of outside of what we can comprehend. So what was so that being said, like, if you traveled far on that balloon to 13.7 billion light years away, like this person said, to the edge of what we can see on the universe, then you wouldn't really get to the edge. You would just get to some more universe. And as far as we know, our current theories of cosmology, again, say that our universe is this infinite flat sheet. And so where if you traveled in one direction, you would just see more universe going on forever over there. So yeah, it's kind of a difficult thing to comprehend, because humans are really bad about thinking about things that are infinite and things that are not contained within three-dimensional space. But the universe is weird.
Well, thank you for that.
Yeah.
So this next question comes from Gary Wiener, and that's again via our email address. He asks, visual representations one sees of the Big Bang, though based on scientific understanding, are presented as viewed from a vantage point outside of the event and therefore look outside of the universe. What would a visualization from inside the Big Bang look like?
So I thought that this question kind of formed a good pair with the last question about the expansion of the universe. And so I was just kind of giving that popular metaphor of the 3D expansion of the universe as a balloon that is blowing up. I think that's usually what people are thinking of when they think of the Big Bang. It's like, a whole bunch of galaxies all starting really close and then slowly getting further and further apart. And that's, I think, kind of the looking in from the outside that Gary is talking about here. So I think that it's kind of good to remind ourselves that, that visualization that I was using before is not totally like accurate. It's kind of looking in from the outside in a way that's kind of artificial. But looking at the Big Bang from the inside, I thought was kind of a funny thing, because, you know, that's kind of what we're doing. We are inside of the universe. We're looking inside what the Big Bang is. So I think a visualization of what the universe looks like from inside the Big Bang is just what you see every day. It's a bunch of galaxies that just look like they're getting further away from each other, and we can't see why, because we can't really see that space is expanding in a super intuitive way to us. So yeah, a visualization inside the Big Bang is just us.
That's kind of cool. I like that.
Yeah.
So this one comes from Charles Johnston, and this is via Facebook, and it's a question about dark matter and dark energy. Are they the same thing? We cannot see it. It's like light. We cannot see it until it strikes something. Photons have energy and therefore mass. No energy. E equals mc squared. Did I say that right?
Yeah.
A solar cell would not work without solar energy. Isn't this what's causing the universe to expand?
Yeah, so this is from somebody who has come up with a theory that the dark matter and dark energy, which are two of the biggest unexplained things in physics and astronomy right now, are just the same thing, light. Because, you know, what we know about dark matter is just that it's some stuff that is heavy. And that's all we know about it. We can't see it. We just know that it's heavy. And what we know about dark energy is that it's some stuff that we can't see that pushes on things. And Charles has made the connection here that, you know, light, you know, according to Einstein's E equals mc squared, energy and mass are interchangeable. So anything with energy, like light, should have some amount of mass. So that maybe means that it could be dark matter. And anything that has mass can push on something and provide pressure like dark energy does. So maybe that means that it can fit the data. And this is something that actually astronomers have considered, whether something like light could be a candidate for dark matter and dark energy. But the more you kind of dig into this issue, you realize that light doesn't really behave in the appropriate way. Light will provide pressure in a way like the radiation pressure that he was talking about here, pressure in a way that can kind of push a spacecraft along like a sailboat in the wind. But that kind of pressure is not the kind of pressure that we observe dark energy to be exerting. So it doesn't really line up with our data there. Although that kind of pressure is kind of what the universe looked like very early on in its infancy, but we're kind of past that in the life cycle of the universe. And then with regards to dark matter, like, you know, light does have some amount of mass energy force to it. But the problem is, the problem is that it's just not heavy enough. Like, if dark matter was actually light, then that means that it would have to be concentrated in these tiny little areas. And if it was concentrated in the tiny little areas that we see dark matter to be in, like galaxies or galaxy clusters, then we would know that it wouldn't be able to escape from those areas. And if we wouldn't be able to escape, then we wouldn't be able to see any light from those areas at all. And it would basically just be a black hole. So it doesn't really line up with the data, but it is a really good connection that, you know, light has these same properties of having energy, but we can't see it necessarily unless we're looking directly at it.
Okay, thank you for that. So the next question is from Ken Maluso via Facebook. And he says, watching the series How the Universe Works, I heard a couple of the scientists say it's the brightest thing in the universe. I hear that a supernova can outshine an entire galaxy. I heard another say that gamma ray bursts are the brightest, and another stated a quasar is the brightest. Which one is the brightest?
So this Ken here is kind of latched onto some of the marketing terms that people like to apply to these various different astronomical things. So the three things that we're talking about here are supernovas, gamma ray bursts, and quasars, which are all these exotic things that, you know, don't happen very often in our everyday lives in the universe. and they kind of have different properties that are associated with how bright they are. So a supernova is when a giant star explodes very violently at the end of its life, and that makes an explosion that's so bright that it is usually brighter than the rest of the entire galaxy that it is in. So this one explosion outshines all of the other stars that were in the galaxy to start out with. And it kind of serves as like a lighthouse, a beacon for us to look at the galaxy for the period of weeks or months that it is super bright. But that's the thing about supernovas, is that they're super bright only for a few weeks, and then they fade away. Meanwhile, a gamma ray burst is a byproduct of a particularly violent supernova. So supernovas are really violent explosions, and then gamma ray bursts are even more violent. And they produce these like super concentrated beams of energy, and they only last for, you know, a few seconds or minutes before they fade away. But in that time, they'll output as much energy as an entire supernova does over its whole lifespan of months or years. So a gamma ray burst is brighter than a supernova because it delivers so much energy packed into a much shorter time than a supernova does to deliver that same amount of energy. And quasars, the third object that we were talking about, are in a completely different kind of class. Rather than being from an exploding star, they're from a black hole that is sucking in tons of material and heating it up into this super bright jet of material that shoots out of it in a super bright beam of energy. And quasars are somewhere in between a supernova and a gamma ray burst in terms of their brightness at a given time. But the difference about quasars is that they are sustained for a very long period of time. So, you know, supernovas only last a few months, gamma ray bursts only last a few seconds, but these quasars can go on for as long as there is more gas to feed this hungry black hole that is shooting off these jets of material. So it's kind of different categories of brightness and different time domains of how we're talking about energy. So yeah, but if you want to be technical about which one is really the brightest, I think that the brightest thing we know about right now is a gamma ray burst.
Nice. Okay, so the next question comes via Facebook, and it's from Brian Forrest Tinio. I hope I said that right. And he says, are black holes actually spherical? And what would that mean for the shape of the event horizon? Would the event horizon be spherical like a shell over the black hole?
So this is a complicated question that's kind of getting towards the edges of our understanding of physics. So when astronomers talk about black holes, or when physicists and astronomers talk about black holes, it's kind of hard because we don't really have a good theory for what a black hole itself looks like. Like, what is the thing that is actually containing all of that mass? We just kind of write it off as a singularity because our physics doesn't really work anymore. Most of the time when we're talking about like a black hole, we're talking about its event horizon, which is kind of this shell, as the email was talking about, that is the kind of where light can't escape from a black hole anymore. So this black hole pulls hard enough that light can't escape from it if you're close enough into it. And that distance where you go from like too close to not close enough is called the event horizon. And these can actually be affected, like the shapes of these are not perfectly spherical all the time. Like, you know, most black holes are rotating just because stuff falls into them and makes it spin up. So it's not totally stationary. And due to some very complicated physics, when these black holes, the singularity in the center is rotating, it will actually drag the space-time around with it and create kind of a squished sphere, kind of like, you know, the shape of the Earth that is squished at the poles and wider at the equator. So that can actually happen, that black holes can be noticeably kind of squished and oblate at the equator. And that's due to the rotation of the black hole that's on the inside. And there are some theories that the shape of the singularity can actually not be like, you know, a point either. It is physically possible to come up with a singularity that is the shape of a ring instead of being the shape of a point, but I'm not really qualified to talk about the details of those theories, since that's kind of on the bleeding edge of theoretical physics at this point, and we can't really test that.
Okay, so I'm looking at the rest of the questions we have left here, and I wasn't sure which one you wanted to do next, because I know that we have a few here in the chat too. So
yeah, I think there were a few here further down that
this one? Okay.
Yeah, so sorry, you can read it.
Okay, so this one is from Andy, and I'm going to have a go at saying your last name, but I'm probably going to get it wrong. Andy Masika. I'm not sure if I said that right, but I tried. And this came via email, and he asks, the twin Keck telescopes appear to be constructed as an interferometer. Are they doing interferometry? Are they capable of examining the structure of the accretion disk around the supermassive black hole at the center of our galaxy?
So this is a very interesting question, and it's a question that is kind of UCO specific here too. So the Keck telescopes are UCO's two big 10-meter telescopes that are on the top of the Mauna Kea volcano in Hawaii. And they were built at the same time, with one of the possible uses for them being an interferometer, like Andy was talking about here. So an interferometer is a special kind of optical setup where you use light from two different places and you kind of smush it together, and using a bunch of complicated optics, it comes out as a clearer and brighter image than you were before. So by combining the light from these two telescopes together, you can create effectively a much larger telescope than you otherwise would have been able to have, which gives you better optical properties when you're looking at small things. So the Keck telescopes were built with this in mind, and so they have like an underground tunnel between these two telescopes, so they can combine the light underground between these two giant observatory domes into one instrument that they can use with both of the telescopes at the same time, kind of like a pair of binoculars. But the problem with interferometry is that it's really, really hard. Like, you have to have everything be perfectly stable. You have to have everything in your system perfectly lined up so that you can combine this light together in a way that's actually useful. And if you are not doing that totally carefully, then it kind of becomes useless. And another problem with this is that for visible and infrared light, which is what Keck is dealing with, it gets harder because the light is just going up faster and faster. And so if you're trying to line it up, then you have to make sure that those two like really fast frequencies are actually going at the same time as each other. So after being in service for about 10 years, this interferometer at Keck was actually able to see some things like distant black hole accretion disks making quasars, like I was talking about before, and some stars that were in the process of forming their planets. But it really was not able to live up to its promise because it was just technically really difficult. And so it's not in service anymore. And about the original question Andy was asking, which was, can we use this to look at the black hole at the center of our galaxy? It's really hard to do that because it's just behind so much dust. It takes a lot of effort to actually get into the center of our galaxy. And by the time we're there, we're looking through so many clouds of dust that it's just not bright enough to really use the interferometer on anymore. So maybe someday someone will be able to rig up an interferometer to look at it like that. But in the meantime, there are radio interferometers that are doing a similar thing to look at the accretion disks in other galaxies, and that seems just as cool to me.
Okay. So this question is from Hoey, and he's a 5th grader from San Jose, and he is asking, are white holes and wormholes possible?
So this is white holes and wormholes. They're kind of things that are popular in sci-fi. a white hole is kind of the opposite of a black hole, where instead of a bunch of stuff all rushing in to a kind of a drain in the sink, it's like something that is spewing out tons of matter in all directions. And these are usually kind of paired with wormholes, which are kind of tunnels through space-time that you could theoretically make. And so the thought is like something would go in a black hole and then come out of a white hole, and all of the stuff that was, falling in there would come spewing out there like a fire hose. So these are theoretically possible, but they also probably don't really exist in the universe. Like a wormhole is something that you can kind of construct mathematically if you use the right equations to make physics do what you want. But if you had a wormhole, then it would probably be open for a second and then it would close immediately, and it would take a massive amount of energy to actually get it open again. So it's probable that these things don't really exist, but they are fun things that you can talk about in your sci-fi books. So I don't think that's I don't think I should take away people's fun by just saying, they're not super practical, because, they're possible, and we've made impractical things happen before.
Well, and what happens in sci-fi eventually makes it in some form or another, right?
Yeah, exactly. I'm sitting here in the year 2020, but who knows where we're going to be in the year 5050 or something like that.
And this is a bit like a tricorder, but I won't get into my fandom of things. Okay.
Yeah.
So moving on. So this question is from Nick Hervey via Instagram, and he says, do magnitude 10 plus moonquakes happen on Io? How would we strengthen a rover to handle such shaking?
So Nick is using the word moonquakes, which is kind of a fun word to think about. Most people haven't really thought about the concept of an earthquake, but somewhere else. And this is something that, geologists, planetary scientists, and astronomers have been thinking about somewhat recently, or kind of in the past few decades, I guess. There are probes that are sitting on the surface of the moon that can tell when there's a small shift in the moon's crust due to the Earth's gravity, or when a meteor hits it on the other side, they feel these little moonquakes that happen underneath the surface of the rover. And then the Mars InSight lander that got there a few years ago was sent there, and one of its purposes was to try to see if Mars had any tectonic activity left, to see if it could feel any Mars quakes underneath it. So yeah, we usually associate earthquakes with volcanic activity and tectonic plates moving around and making big things happen. And Io is kind of a poster child for that in the solar system. Io is the closest big moon into Jupiter, and Jupiter pulls a lot on it and shifts everything around. And there's a lot of volcanoes and lava spewing everywhere on the surface of Io at any time. So it's possible that there are some very large Io quakes that are out there. And if you were to try to put a rover on there, I think it would probably be okay, because it's not like cars will just fall apart when they're in a giant earthquake. They mostly just sit there and rattle around a little bit, and then you're okay. And even then, in order for a rover to make it to Io, it would have to sit on top of a big rocket to get there, and a rocket is going to shake you a lot more than a given earthquake, I'm guessing. So I think it would be okay. We wouldn't have to worry about the rovers so much, but it would provide geologists some really cool stuff to think about if they could get all that earthquake data from another planet.
Oh, that's fantastic. I just love how much, the talk about astronomy and the universe excites people's imagination.
Mm-hmm.
These questions are just super interesting. Okay, so this one is from Amelia, and she's asking, what got you interested in astronomy, and what local events can help someone without much experience to know what to look for in the sky at night?
Mm-hmm. Yeah, I have been interested in astronomy for a super long time, but I always give credit back to my middle school science teacher, who did a whole unit on astronomy when I was in 8th grade. And one of his assignments that he gave us was to once a week just go out and look at the sky for 15 minutes and write down what you find. And while I was out there looking at the sky as a homework assignment, there was a bunch of interesting stuff that I saw just because I actually had to take the time to sit there and look at it. And that got me interested in all sorts of things from there. So he's usually what I trace myself back to. And, you know, why am I an astronomer today is because I got interested in it in middle school. But as far as local events for learning about astronomy, I would say that if you're submitting questions to this, then you're on the right track already. But another good resource to use for local events for getting interested in astronomy are local astronomy clubs. So I grew up on the peninsula, and there's a Peninsula Astronomical Society that meets normally every month or so and brings a bunch of telescopes out to a given park somewhere, and then people can go and look through the telescopes and ask questions. And I know there's a San Jose Astronomical Society too, so I don't know where Amelia lives, but chances are if you Google, like, you know, whatever astronomical society, then you can come up with something, and hopefully they'll still have some sort of event that you can go to nowadays in the pandemic.
So Amelia also asked the burning question that I get asked at least 2 or 3 times a week via email is, when will Lick Observatory be open to the public? And obviously this is a very fluid situation that we're dealing with, the COVID that we're all you know, experiencing. And at the moment, Lick Observatory continues to be closed to the public, but the staff are working on opening some of the outdoor areas to the public, which could be in the next couple of weeks, but that will very much depend on what happens in the next couple of weeks. So for the time being, the visitor centre will remain closed until indoor museums are allowed to open as per the state and the county. And, you know, we'll be watching the public health announcements, and we'll keep you informed via our social media networks and also the website. But hopefully in the near future, that will be a possibility. So I just wanted to add that. We're going to move over to some of the questions that we've got in the chat here. I'm going to scroll up a little bit here. Let's see. So somebody commented, Brian, that your lighting isn't very good. And I just want to say that I pointed that out in the beginning.
Yeah, sorry. My home setup here isn't super well optimized for Zoom calls. It's been a problem over the past few months.
Okay, so the first question here in the chat is from Brandon Bagwell. And he said, if I wanted to research a particular comet in the future, how can I find the best time of year to view it? Would it be during the comet's perihelion? Or when it's closest to Earth, or something else? Comets don't visit us on the same ecliptic the planets travel on, and I'm unsure how best to plan my next comet chasing trip.
Yeah, so this comet that, well, okay, let me give a caveat first. Comets are unreliable. Comets are essentially these kind of loose, dirty snowballs of stuff that are flying through the universe, and you know, we can predict with a reasonable amount of certainty where they will end up at a given time, but we can't really predict very well what they'll look like when they get there. So there have been a number of comets that have kind of fallen into the inner solar system over the past few months and swung by the sun, and people are saying, okay, if this comet, you know, comes out the other side, then it'll look really cool and bright and nice, but then it turns out that it just melted and there was nothing left afterwards. So I would hesitate to plan for anything comet related in 2024 because a lot can happen to that comet before then. But that being said, if there is a comet that actually does end up panning out, usually the best time to look for it is somewhere between the perihelion, which is when it is closest to the sun, and the point before or after when it is closest to the Earth. the perihelion is when it's going to be the brightest because the sun is, melting it the most and shining the most light on it. But it's harder to see because you have to look really close to the sun to see this comet that is now suddenly really close to the sun. So my advice for looking for comets is wait and see how it actually turns out before you make any big plans. Because like this comet, you'll probably have a few days or weeks to figure out what you want to do to go look at it afterwards. After you know that it has actually, survived the plunge into the sun, and you will be able to see it. Because otherwise, if I had planned big trips to go see all the comets that people said were going to be great, then just this year I would have already had to take 3 trips, and 2 of them would have been busts. So yeah, that's my advice on comets.
Lots of patience required for astronomy.
Exactly, yeah.
Okay, so this is from Bob Kelly Thomas, and he says, how would you compare the eclipse observation results of the 1919 British and 1922 Lick Observatory in terms of proof of stellar light deflection near the sun as predicted by Einstein's general theory of relativity?
So a little bit of history for people that are not as up to date on their astronomical history as this question asker. Einstein's theory of relativity, which was published a little more than 100 years ago, was one of the predictions that it made is that heavy things should be able to bend light as the light passes it by. So if you were to look next to the sun, then you would be able to see a star, kind of the star's light going past it, and then as it goes by, it would get bent off in one direction. So the star wouldn't be in the position that you thought it should be in. So the problem is usually you can't see stars that are right next to the sun because the sun is too bright and it kind of drowns them out. But during a solar eclipse, you can actually do that. And so there are some very famous expeditions to places on Earth where there are total solar eclipses by different observatories to take pictures and compare them with how much they thought these stars should be being bent and how much they actually were observed. And they found kind of broad agreement. I've heard that some of these observations are not necessary. There are more errors in them than they originally thought. These were people that were, in the case of the 1918 eclipse, lugging a telescope out to the middle of Eastern Africa and using these like glass plates smeared with photographic chemicals to take these pictures. And so it wasn't necessarily as exact of a science as they wanted it to be. But so there might be some error in there that is not the same precision that we know general relativity to nowadays. But in general, those kinds of observations should work. And whether you're at Lick or whether you're in Eastern Africa, you should be able to see some amount of bending of light if you're in the right conditions.
Okay, thank you. I see everybody's still hanging on in there, so I'll ask a few more questions. Okay, this next one comes from Bali, and he says, or she says, evidence confirming gravity waves was detected a few years ago. Is there current research being conducted in this area?
Yeah, so gravitational waves are another thing that was predicted by Einstein's general relativity 100 years ago. But this consequence was not actually detected until a few years ago, I think in late 2015, and then everything was published in 2016 by the LIGO experiment, which is it's a set of 2 giant detectors, one in Washington State and one in Louisiana, that were looking for gravitational waves, which are these tiny distortions in space-time that result from 2 black holes that merge together and kind of send out these ripples that are really hard to detect, but are there. So astronomers were very excited about this because it's hard to know anything for sure about a black hole. And so if you can get a good observation of anything from a black hole, like these gravitational waves, then you can, confirm or refute a lot of theories that otherwise were really hard to test. So astronomers have been really excited about this. And so if there's some gravitational event that they detect, LIGO, the detector that started this, is still operating, although it's in a break right now. So it will detect a wave going from somewhere, and then people will go point their telescopes over there and see if they can find something. And in one case, they did find a team of astronomers at UC Santa Cruz found two merging neutron stars there, and they were able to observe a new class of event called a kilonova that had never been observed before. So that was a really big thing that has come out of this. But yeah, there's still a lot of research kind of going around in this area of gravitational astronomy, and there are some new detectors that are planned to come online relatively soon in the next few years that should make our measurements of these gravitational waves more precise. And then in the 2030s or so, there's going to be a set of satellites to detect kind of a whole different class of gravitational waves. So, give it some time. Physics kind of moves slowly because it takes a long time to build these big and ambitious experiments. But I think cool things will come out of it eventually.
It's that patience again. Okay, so this one comes from Al Kwan, and the question is, are we any close to resolving discrepancies in different methods of measuring the age of the universe?
So this was figuring out the age of the universe was a problem, I would say maybe 20 years ago. There were different ways of kind of figuring out how old things were. You could look at the oldest star that you could find and say, how old is that star? And then that the universe is probably around that old. Or you could look at, we know that the universe is expanding, and if we can measure how fast it's expanding, then we can just press rewind and see when it went back to the beginning. And we can get a good idea of, how long the universe has been around just by that. But more recently, people have gotten pretty good at figuring out how old the universe is. Now our margin of error is down to, maybe 100 million years or so. So this isn't really that much of an active field of research in astronomy anymore. It's something that we have a pretty good handle on. Now that uncertainty that we're working on now is figuring out exactly how fast the universe is expanding, because if you measure it one way, it looks like one speed, and if you measure it another way, it looks like another speed, and they're in tension with each other. And this is, if you talk to a cosmologist right now about the biggest disagreement in the field, then that's it right now. So we've moved on to smaller and more minute disagreements, which I guess is the steady march of science.
Okay, so I'm going to ask one more question. You can see the chat, can't you, Brian? Is there one
Yes.
that you would like to select as your last?
Let's see. I was looking through, and I liked Barley's question from earlier about gravitational waves. Let's see. Oh, yeah, okay. Here's a kind of more practical question from Patty. In the Bay Area, where is the absolute best place and time to see the Milky Way? So my recommendation is, there's a lot of mountain ranges in the United States. And so if you can get one mountain range away from major cities, then usually you have a much better time looking at the sky than you otherwise would. A lot of times the coast kind of between Santa Cruz and Half Moon Bay is a good place to go, although it's oftentimes foggy. But it's pretty rural out there, and there's a mountain range separating you from the Bay Area. So if you look out over the ocean, you can get pretty dark skies as long as it's not foggy on that day. I've heard also that at Lick Observatory on nights when the fog is so thick that it comes in and covers all of San Jose, that it gets super, super dark up there because all of the Bay Area is effectively under a blanket, and so there's no light pollution for it to ruin your view of the Milky Way. Other places that if you move a little bit further out that you can go look, if you go up or down the coast a bit to past Santa Rosa or south to Big Sur, then you can get better skies because you're further away from stuff. Or if you really want to get a good view of the sky, going up to the Sierras or out to the middle of the Nevada desert is really the top-notch thing to do. I when I was in high school, went out to the middle of the Nevada desert and I was like, 50 miles away from the nearest town of like 3,000 people. And it was completely dark. It was a like whole other level of dark that I have not experienced since then. And I really recommend it, that if you want to go out and see the Milky Way and all of its like glory, to go out and find somewhere super dark. And if you bring a telescope or a pair of binoculars, you'll be able to see a lot of cool stuff.
What a fantastic comment to end on. Thank you so much, Brian, for today. Your enthusiasm, just shines through. It's been an absolute pleasure having you on. And I just want to thank everybody for continuing to support us week after week. It's so great to see you all here, and I'm getting to recognize your names and your faces. I want to let you know that next week on August the 3rd, we will have Dr. Ryan Foley, and his work examines dark energy and how it drives the expansion of the universe. So that should be super interesting too. So I hope you'll make time to join us next week. I had a couple of people who came on late and were asking how they can watch the whole thing. And I do upload these to our YouTube channel. And so if you want me to send you the link for the upload, you can email me at social@ucolick.org, and I will send you the channel link. Please subscribe. That would be great. Then you'll get notices of all the other uploads we do. So thank you so much. Remember, you can send questions to us anytime. And when we stop doing this particular type of event, then you'll be sending your questions directly to Brian, and now you'll know the face to the person who's going to be answering those questions for you at our UCO Ask-an-Astronomer. So thank you so much again for joining us. It's a pleasure to see you all, and hopefully we'll see you all next week. Thank you. Goodbye.